They came back standing. That was the first thing the recovery team noticed. All four of them, upright, walking, waving at cameras. The kind of images NASA needed the world to see. But that's not the whole story. It never is. 10 days. That's how long Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen spent beyond low Earth orbit further from this planet than any human beings had traveled in over 50 years. The media covered the launch, covered the splashdown, covered the handshakes and the flags and the press conferences. What they didn't cover, what rarely gets covered, is what the mission actually did for human bodies at the cellular level. Let's be precise about this. Space is not a place humans were built for. Every system in your body, cardiovascular, neurological, skeletal, immune, visual, evolved under one assumption: gravity, constant, downward, 9.8 meters per second squared. Remove that assumption and the body doesn't adapt. It unravels. Slowly, systematically, in ways that are still not fully understood. 10 days is long enough to begin the unraveling. Start with the fluid. On Earth, gravity pulls your blood and bodily fluids downward. Your circulatory system is tuned for this. Your heart pumps against it. Your veins and arteries are calibrated to it. The moment you enter microgravity, that downward pull disappears. The fluid shifts upward. Within hours, not days. Hours, roughly 2 liters of fluid migrate from the lower body toward the chest and head. Astronauts describe it as feeling permanently congested, like the early stages of a cold that never develops and never resolves. Their faces swell visibly. The veins in their necks distend. Pressure builds behind the eyes. This is called fluid shift. It sounds manageable. It isn't. Here's what that actually means. The optic nerve sits inside a sheath filled with cerebrospinal fluid. That fluid, like everything else in microgravity, has nowhere to drain, so pressure builds slowly, steadily against the back of the eye. The eyeball flattens. Not dramatically, not visibly, but measurably. The posterior globe of the back wall of the eye deforms under sustained intracranial pressure. The optic nerve itself can swell. Folds appear in the choroid, the vascular layer beneath the retina. The fovea at the precise center of your vision can shift. This condition has a name: Spaceflight-Associated Neuro-ocular Syndrome. SANS. It was only formally identified and named in 2016, despite humans having been in space since 1961. Think about that for a moment. Decades of spaceflight, decades of astronauts returning with degraded vision, and the medical community didn't have a name for it, a mechanism fully understood, or a reliable solution. Until the 21st century, the Artemis II crew underwent extensive ophthalmological screening before and after the mission. The results have not been fully published. What has been confirmed is that intracranial pressure monitoring was part of the mission's medical protocol, because the risk was considered significant enough to track in real time. And then something happened to their bones. In microgravity, the skeleton receives no mechanical loading, no weight to carry, no resistance to push against. Bone is a living tissue. It responds to stress by reinforcing itself. Remove the stress, and it stops reinforcing. It begins to thin. Studies on International Space Station crew members who spend 6 to 12 months aboard show bone density losses of 1 to 2% per month in weight-bearing regions. The hip, the spine, the femur. Losses that would take years to accumulate in an elderly person on Earth happen in weeks in orbit. 10 days is not 6 months. But 10 days is not nothing. The deterioration begins within the first 24 to 48 hours of microgravity exposure. The osteoclasts are cells that break down bone tissue become more active. Almost immediately, the osteoblasts are cells that build bone slow down. The balance tips. For a 10-day mission, the losses are considered acceptable. Recoverable. NASA's own language around bone loss uses the word manageable. But here's the problem. The Artemis program is not planning 10-day missions indefinitely. The architecture is designed to extend lunar surface stays, gateway station rotations, eventually transit to Mars, a journey of 7 to 9 months each way. The Artemis II mission was not just a flight. It was a data collection event, a physiological stress test for what comes next. What the crew's bones experienced over 10 Days is a preview of what future crews will experience over 10 months. The muscle follows the same logic. Without gravity, the postural muscles are the deep stabilizers of the spine. The calves, the lower back, have nothing to stabilize against. They atrophy rapidly, measurably. Astronauts on long-duration missions lose up to 20% of their muscle mass without rigorous countermeasures. The Artemis II crew exercised. The Orion capsule had a resistance exercise protocol built into the mission plan. 2 hours of physical countermeasures per day, a number derived from ISS experience. The minimum considered necessary to slow the deterioration. Slow, not stop. Even with daily exercise, muscle loss during spaceflight is not fully preventable with current technology. The body, in the absence of gravity's constant low-level demand, simply begins to shed tissue it calculates it no longer needs. It's efficient, ruthlessly so. Let's be precise about what the heart does in space. On Earth, your heart is a machine optimized for fighting gravity. Every beat is calibrated to push blood upward to your brain against the downward pull. In microgravity, that workload decreases. Blood reaches the brain more easily. The heart doesn't need to work as hard. So it doesn't. Within days, the heart begins to decondition. It shrinks slightly in mass. Its output per beat decreases. The cardiovascular system, like the skeleton and the muscles, adjusts to its new workload, which is lower. The problem arrives on return. The moment the Artemis II capsule hit the water, the moment gravity reasserted itself, for deconditioned cardiovascular systems suddenly had to perform at full Earth capacity again. This is called orthostatic intolerance. Stand up too fast after lying down for a long time, and you feel it. Briefly, the head rush. The slight dimming of vision. Astronauts returning from long missions experience a version of this that can last weeks. The heart, shrunken and deconditioned, struggles to pump blood back up against a gravity it has partially forgotten. Some returning astronauts cannot stand unaided for the first several hours after splashdown. The Artemis II crew walked, but what no one discusses is what their cardiovascular systems were doing internally during those first hours, working against a gravity that had become, in a measurable physiological sense, slightly unfamiliar. And then there is the radiation. Low Earth orbit sits inside the Earth's magnetosphere, a vast magnetic field that deflects most of the high-energy particles streaming in from the Sun and from deep space. The International Space Station operates within this protection. Most of the human spaceflight experience we have accumulated over 60 years exists within this shield. The Artemis II trajectory went beyond it. For a portion of the mission, during the transit around the Moon, the crew was outside the magnetosphere's protection, exposed to the full spectrum of galactic cosmic rays and solar particle radiation in a way that ISS crews simply are not. Galactic cosmic rays are not the radiation of a medical X-ray. They are high-energy atomic nuclei, sometimes iron nuclei, traveling at a significant fraction of the speed of light. They pass through spacecraft walls. They pass through flesh. And as they do, they leave a track of ionization, a microscopic trail of cellular damage through whatever tissue they traverse. The DNA in cells along that track is damaged, sometimes repaired, sometimes not, sometimes repaired incorrectly, which is its own category of problem. For a 10-day mission with careful solar weather monitoring, NASA's models suggest the radiation dose received by the Artemis II crew was within acceptable career limits, within guidelines. But here's what that actually means. Acceptable career limits is a risk management category, not a guarantee of safety. It means the additional lifetime cancer risk associated with the dose is calculated to remain below 3% above baseline. That is the threshold NASA uses. It is a bureaucratic number built around an ethical compromise. Because there is no dose of ionizing radiation that carries zero risk, there is only risk deemed acceptable for the purpose of the mission. The Artemis II crew accepted that risk knowingly, professionally, with full understanding of what they were absorbing. That does not make the absorption less real. There is something else, something that doesn't appear prominently in the physiological literature, but that astronauts consistently describe when they speak candidly. The psychological weight of distance. At its furthest point, The Artemis II trajectory took the crew approximately 10,000 kilometers beyond the moon and further from Earth than any human beings had been since Apollo 17 in 1972. At that distance, the communication delay with Earth is minimal. Light speed signals still travel fast enough for near real-time conversation, but the visual reality is different. The Earth, everything now becomes a disk, a small, luminous object in a field of absolute black. Every person the crew had ever known, every structure ever built, every crisis and history and warmth that defines human existence, compressed into something you could cover with your thumb. This is not metaphor. This is a documented perceptual phenomenon that alters cognition in measurable ways. The overview effect, described by astronauts since the earliest orbital missions, involves a profound and sometimes disorienting shift in perspective. Some describe it as clarifying. Others describe the return as the harder transition of coming back into a world that now seems, irrationally but persistently, smaller than it did before. The Artemis II crew has undergone months of post-flight medical evaluation since their return. The data being collected are blood panels, neurological assessments, vision tests, cardiovascular stress tests, bone density scans. Psychological evaluations is not primarily about them. It's about the people who come after them. Every piece of physiological data collected from those four bodies is feeding the models that will determine protocols for Artemis III, for the lunar surface missions, for the eventual Mars architecture. They were not just astronauts on a mission. They were, in a clinical sense, test subjects, willing, decorated, courageous test subjects for the question of whether the human body can tolerate what we are planning to ask of it next. And the answer, so far, is probably, with conditions, with countermeasures, with acceptable levels of managed risk. They came back standing. That image was real. The smiles were real. The pride was real. But somewhere in the data, in the bone scans and the retinal photographs and the radiation dosimetry records, is a quieter story. The story of what those 10 days cost at the cellular level, at the physiological level, in the slow, systemic way that space extracts its toll from every body that enters it. We are learning what that cost is. We have not yet decided if we fully understand what we are asking people to pay.